how can we do long exposure astrophotography using an alt-az mount? So a mount that can only move or rotate horizontally and vertically. We know it's possible because a lot of professional observatories with huge telescopes have their telescopes set up effectively in alt-az mode, and there's some very expensive equipment from things like PlaneWave that also uses by default without a wedge alt-az for astrophotography. And when I started astrophotography, I actually started with an alt-az mount, but I was limited to pretty short exposures because afterwards I would get a phenomenon called field rotation. And yet, this year at NIF, it seems that Prima Luce, or what is it, the Prima Luce, has decided that alt-az astrophotography is back in fashion because we don't like doing polar alignment. We don't like setting things up. We just want to roll the scope out and press a button and then it's imaging, which, you know, makes sense as well for smart telescopes. Some smart telescopes don't even support equatorial mode yet, like the Vespera smart telescopes, and they have a lot of cool software engineering to make alt-az work anyway. And the Sea Star does that as well. The Dwarf does that as well, though they have the option to be used in equatorial mode. And so I've been falling into this black hole of how can we make it work for normal amateur equipment. And so I started to look into it, and I kept looking into it, and I fell into the black hole of looking into it. I'm currently in the state of spaghettification at probably, or I don't know when, I'm probably at the event horizon or something like that. So I wanted to make this video to show you a bit what I found and some of the questions remaining for me, especially when it comes to things like flats. That's the only thing that's kind of like unanswered for me. So let's get back to the start. What caused this thinking, and what does the maker of that equipment actually tell us to do? Okay, so what started all of this is this guy here for me. This is Prima Luce. They showed off this during NIF, and it's one of the things that I hadn't really, thought about it or even like noticed it. I didn't mention it in my video about NIF because I'm like, alt-az, you cannot do proper astrophotography like that, you plebes. But obviously, I'm completely wrong. I mean, I'm exaggerating. I didn't react like that, just to be clear, but whatever. We have this guy here, which is a CBC 8-inch Schmidt-Cassegrain telescope on alt-az mount. By all accounts, it's awesome. I've used alt-az stuff for a lot of things, including visual, mostly visual astronomy. I love them. They're amazing overall. So how does this work? Well, we mentioned that there is field rotation. Actually, I'm gonna skip ahead and show you something, a paper with tons of math, but that shows you an example of a picture across time of Orion, of the Orion constellation, if you're tracking the center star of Orion's belt. And you can see that with time, if you're tracking it in alt-az, Orion will rotate, so that if you had taken a single long exposure for that whole period of time, what you would see is all of those red dots connected here as a line, as a line, as a line, as a line, etc. in terms of star trails. And the only star that wouldn't have trailed is this guy here, right? That's what you can expect to see if you don't do anything. So what can you do about it? You can add like this guy here, this red thing here in the middle, a derotator, or a rotator that can derotate. Basically, we have this phenomenon of field rotation, right? We know where we are pointed at, so we know how to derotate that thing because we know the exact rotation speed, right? So let's just counteract it with another motor. There's an obvious inconvenient fact about that is that to track objects, you now need to move the azimuth axis, you need to move the altitude axis, and you need to move a third motor, the derotator, right? So you have three motors working instead of one, technically, when doing astrophotography on an equatorial mount. Although, we know when we guide, we also guide in declination because not perfect polar alignment, etc. So it's 2 axes versus 3 effectively. And the third one, the derotator itself, well, it doesn't matter that much because as long as it has a proper, somewhat decent encoder in there, it should be able to derotate pretty well. So overall, it doesn't sound like a bad idea. But once, if we ignore the fact that we're now using 3 motors instead of 2, there's the elephant in the room here. We are having a Schmidt-Cassegrain telescope with a very long focal length compared to the telescopes that I typically use and show on this channel. And so guiding is very, very important because we want to track our targets very, very well. So how can we do guiding with that telescope here? Well, for that, let's ask Primaluce and their manual directly, right? So I'm opening the manual with the guiding, and what they tell us is something very interesting. You may have read that off-axis guiders are often recommended for long focal length telescope, like the Edge HD optics used in the CPC Deluxe HD 8-inch, right? An off-axis guider picks up a guide star from the same optical path as the main camera, which eliminates any flexure between the guide telescope and the main telescope, which is all true. I've already talked about that in previous videos. It's very important actually to eliminate flexure if you're going to do narrowband imaging, especially at such slow focal ratios, meaning you'll probably take like 10 minutes exposures. But let's keep going. However, with an alt-as fork mount, an off-axis guider is not a practical option since a camera mounted laterally on the optical train would inevitably collide with the fork arms during telescope movement, because we continuously rotate the imaging camera to correct for field rotation. If I go back to this picture, I'm thinking, really? 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 Like, would it actually collide anywhere if we have like a small enough off-axis guider? I don't see it. I don't see this as a valid excuse. There's another reason, and it has to do with PhD2. And I had to go and look at the code of PhD2 to convince myself of it, but we'll get back to that later. I'm so sorry, this is going to be such a nice black hole of information I'm sharing with you. It's such a geeky video, but I'm sure I'm not going to get a lot of views because I don't get a lot of views on geeky videos. So if you want to help me out, please watch this until the end. Please leave a like. Please leave a comment if you had experience, for instance, imaging in alt-as mode and how you made it work. And if you want to support me even more, and you're planning on buying anything from Agena, High Point Scientific, Amazon, lttstore.com, if you do so after clicking the links that I have down in the description, it will help me out at no cost to you. And of course, you can become a Patreon member, a channel member, link in the description, or it's the join button next to the subscribe button to make all of these videos possible directly to become a sponsor of the channel. You guys make everything possible. Thank you so much. Anyway, let's keep going. So it's probably might not be the main reason. Maybe it could collide with this focuser here on the side, but then you have an option where you're using an in the imaging train focuser as well from Primaluce. So I don't see that as a valid reason. But okay, whatever. Let's keep going, right? So they tell us effectively that we need to use a guide scope. Okay, so we use a guide scope, and the advantage of using a guide scope is that we can basically deceive PhD2 into believing that it is doing equatorial mode kind of guiding, because the axis will always be vertical and horizontal. They even tell you that you want to make the camera itself have the sensor be either like oriented like this little orange square rectangle here, or that little or rectangle there, so that we have like it's nicely aligned on the pixel so we can get the best guiding possible. Okay, good. But there's more stuff, right? Because there's something very important that they make a good point mentioning, is that the guide telescope must be perfectly parallel to the main telescope, and the guide star must be selected as close as possible to the center of the field of view of the guide camera, which is also very important, because remember that diagram here with the field rotation of the Orion constellation here. Well, that star at the center, it's actually the star that we're guiding on. So imagine you're trying to take a picture of the Great Orion Nebula and the Running Man, let's say around here, right? But you're guiding on the central star of the belt. Well, you'll get field rotation on your target because you're not guiding at the center of the field of view of your main camera. So you would need to actually make sure that you collimate, you align your guide scope and your main telescope so that you point at the same thing. So you'd probably spend a session going like pointing to Vega or to some bright star and make sure that the center of your guide camera is the same as the sensor as your main imaging camera. And then when you select a guide star from PhD2, you want to make sure that you select a guide star that is as close as possible to the center of the field of view of your guide camera, because otherwise you can get field rotation. So that is a very important point that, it's nice that they mention it, because it is indeed very important and gives us a first element of response about why an off-axis guider might not work well, because by definition, an off-axis guider will use a guide star that is away from the main imaging sensor. How much does that impact us on a very long focal length? Actually, not much. Because, again, going back to this guy here, this guy made a lot of computation. By the way, if you open, I'll have all of the links down in the description. Don't forget to click on more pages to see all of the nice computations. By the way, don't be too scared. It's mostly simple trigonometry and matrices, and a lot of the stuff is just like boilerplate formulas about how to do a rotation transformation matrix around a specific vector of given coordinates. It's pretty basic stuff, and there's some very interesting as well assumption, for instance, that the time difference between your points is small, that kind of stuff. But it's a fascinating little paper. I'll have the link in the description. And one of the things that it tells us is that probably for long focal lengths, the fact that we're guiding on an off-axis star shouldn't be such a huge issue. So off-axis guider is not completely disqualified based on that. It also tells us, by the way, that imaging near the zenith is probably not great, because then you have one of the axes that could actually reach the necessity of rotating at infinite speed, which, it's not the case in real life, but it's one of the reasons why the C-STAR and other smart telescopes in alt-az mode don't really like imaging near the zenith. Anyway, fascinating paper. I'll have the link down in the description if you're interested, and I really love this little diagram because it really shows us field rotation around the star that we are guiding on. Okay, now going back to the secret sauce, which is not secret because a lot of people have been doing that in the past already, but the documentation from Prima Luce is PhD2 guiding, right? So they tell us, like, once we set up PhD2 guiding is the new profile wizard, and under the guide camera, we choose our guide camera, etc. Everything's gonna work, and then they tell us how to connect to the mount via ASCOM so that PhD2 has access to the mount. And because we're using a guide scope rather than an off-axis guider, we don't connect to the rotator or derotator, because the guide scope itself, it's fixed in place. It's always going to move vertically and horizontally. That way we can deceive PhD2 without needing to give it rotation information. In fact, we must not give it rotation information. So it's actually critical to not connect the rotator to PhD2 in this case. Now they point out the very important settings to have in PhD2 then is that for both right ascension and declination, instead of for declination what we usually have, which is the resist switch algorithm, we need to use the same algorithm as is normally used for right ascension in equatorial mounts, which is this guy here, hysteresis. And we use it for both axes. And this is because both axes basically perform the role of right ascension from the PhD2 perspective. Okay, and then they tell us, make sure to uncheck multiple stars. So that's a huge drawback. We've already seen that to use this prima luce system, we have to give up on avoiding flexure, right? Which means that we could be affected, even if we have perfect guiding, by some weird elongated stars if we go for very long exposures in narrowband, for instance. I would love for someone to get that equipment and test that with long 15 or 10 minutes long exposures in narrowband. And then we have a second issue, which is that we have to uncheck use multiple stars, which has been a huge boon in PhD2. It's made guiding much better because it allows us to average the seeing of a single exposure across multiple stars, gives us better guiding figures and better guiding overall. So now we have to take that advantage of normal guiding with an equatorial mount away as well. And the reason is simple, because your guide scope has a fairly wide field of view, which means that your guide scope will be affected by the rotation. Your guide scope doesn't have a derotator, right? So it will be affected by the rotation of the stars that are outside your primary guide star. Within the guide scope, we'll be seeing something like this, right? So if your guide scope has this guy as the primary star, and then it uses multiple stars to get information from all of the others, it will try to average the changes between the stars because it doesn't know that it's in alt-az, right? PhD2 believes it's equatorial mode, and then it will basically give spurious, incorrect guide commands to the mount. So no, we cannot use that. And then simple stuff, we don't use deck compensation, we don't reverse the declination output after the meridian flip because there is no meridian flip. We're in alt-az, which is one of the big advantages that we have here. But you can see there's already, in terms of guiding, a lot of trade-offs. And then in their documentation, they are very clear, and this is actually very, very good, of the two critical requirements for successful guiding, which is that we need to select a guide star as close to the center of the image as possible. Otherwise, we'll still get field rotation, right? And they even tell us that if no suitable star is visible near the center, slightly move the telescope position in respect to the target. For not too weak galaxies like M81, you can even use the galaxy core to guide, right? So this is another issue of that kind of setup, is that now we actually have to change our framing of our target to basically agree with what we can guide from, right? So we have another constraint on what we're able to do for the advantage of having a very simple alt-az setup, which is still pretty interesting. And then they tell us that the guide scope and the main telescope must be perfectly parallel. And they probably tell us that if the two telescopes are not parallel, the star that PhD2 is monitoring and the guide camera will not correspond to the same area of the sky that your main camera is imaging, making guiding ineffective. Also, the derotation rate chosen by the main imaging sensor will not agree with the star that we are actually tracking on which the derotation should apply to, right? This could be somewhat resolvable by software, but because we're using standard software that is not made for this purpose, it's not without some custom software there. So I thought this was fascinating. And there's the rabbit hole or the black hole goes deeper, right? Because we've already established that likely, I don't know, I would need to double check this, but the clearance for the off-axis guider might not be the real reason why we cannot use an off-axis guider. We've already seen, at least based on my understanding of this paper here, please, math people, double check it for me and tell me if I'm wrong, that with an off-axis guider, even though we're using an off-axis star, we're probably fine in terms of the derotation for long-ish exposures. So what could be the real reason that we cannot use an off-axis guider for guiding in PhD2 with an alt-az mount? Well, for that, I went down the rabbit hole of the PhD2 source code. And don't worry, you don't need to understand how to code. I'm going to make it very easy. Basically, in PhD2, there's a rotator, right? So PhD2 connects to your rotator. And one of the important things that it does is this thing here. It takes the rotator position from your rotator. Even there's even like events that listen to rotation changes, right? So PhD2 is always aware of your rotator angle, right? Or in our case, it would be the derotator angle. which sounds like it's good enough, right? It should be able then to keep track of the derotation. And then what PhD2 does actually is that it has a function under its mount actually implementation that it adjusts the calibration for the scope pointing, which includes taking the rotator angle from the hardware rotator, so this guy here, right? So we take the rotator angle, and then it does a lot of stuff in there with the rotator angle. What it does is it takes your current calibration and just transforms it to take into account your rotation, right? If you're using ZWCAA with PhD2 and Nina or ASI Air, and you're rotating between targets, this is what PhD2 will do. It will transform the calibration data to adjust for the rotation. It doesn't do a recalibration, right? Now, the very important thing here is when does this transformation of the calibration data based on the rotator angle happen? Well, for that, there's something else. This is the guider CPP, basically the whole guider routine, the most important part, arguably, of PhD2. And in there is this very important line. It's basically the only place where this adjust calibration for scope pointing is called for the mount, in addition to this. But this, when PhD2 says secondary mount, they mean adaptive optics, actually. So we can completely ignore that. Plus, in adaptive optics, PhD2 ignores rotation because it assumes the glass of your adaptive optics rotates together with the camera sensor. So we're looking at only this. So only this, in this case, do we transform the calibration coordinates of the calibration data to take into account your rotator position. When does that happen? It happens in a longer function, which is when your guider has a new state. For instance, guiding is stopped, guiding is started, etc. That kind of stuff. So the guide state changes, and it tells us that if the new state of guiding is guiding, meaning that you manually started guiding, or Nina or the SI Air asked PhD2, because the SI Air also uses PhD2 in the background, by the way, asked PhD2 to start guiding, then we hit this. So PhD2, before it starts guiding, it looks at your rotator information, it transforms the coordinates of the data from your calibration to adjust to the new angle of your rotator, and then it starts guiding. What is very important is that it does it only once when you start guiding. So if you're having like a schedule where you're imaging multiple targets and you change the rotation angle of your camera in between targets, your software, whether it's the SI Air, Nina, or something else, will stop the guiding, slew to the new target, change the rotation of the new target, and then start the guiding again. When it starts the guiding again, PhD2, bam, it adjusts, it transforms its calibration data for the new angle without doing any recalibration, right? Notice the problem. If you're using a derotator, your angle changes constantly while you're guiding. And so PhD2 is not able to support a derotator with constant derotation. So it would need to basically call this function, this adjust calibration for scope pointing function, after every single guide exposure to transform the calibration coordinates and or the calibration data so that the guiding can happen properly with derotation. If it did that after every single exposure, then it should work decently for derotation. But currently it's not possible, and I suspect that's the real reason why Primaluce decided that, okay, PhD2, it's not going to work with an off-axis guider with a derotator because PhD2 simply does not have the structure in place to support that. That said, PhD2 is called Open PhD guiding for a reason. It's because it's open source. And that's why we have a version of it in the SI Air. That's why we have, I believe, a version of it in the Tube Text de la Vita, that kind of stuff. So it means that technically anyone, including Primaluce, could go in there and make their own branch of PhD2 that supports changing the calibration data for your derotation after every single guide exposure before starting the next guide exposure, or even while starting the next guide exposure, but before the next adjustment is done based on the data from the next guide exposure, right? It can be done and shouldn't be too insanely difficult to do that. So I thought that was very interesting. By the way, while I was digging into that black hole, I saw like some old threads, like what, 16 years ago almost, with people using a Meade telescope with a derotator and getting super cool images of galaxies like that. Let me tell you, in 2010, that wasn't easy. So mad respect to Marquinhos, I guess, for that. Amazing. And then even when I searched all around, and there's an on-step, so that's like a mount firmware and driver that's used by stuff like the SAL33 from ML Astro. On-step has some code that was added, I think in 2024 for alt-azimuth drives. Like if you're using pulse guiding and your mount type is alt-az, or alt-at, whatever that means, then do whatever this does. I have no idea exactly what's going on, and I suspect that this is for that reason, meaning that maybe on-step mounts, which obviously the Celestron CPC isn't, might work way better for alt-azimuth guiding than other mounts. I don't know. Again, I'll have all of the links down in the description. So if you can understand what's going on here, or you're involved in on-step in any way, please tell me exactly what's going on. But I suspect that's actually the case. It's basically like PhD2 will always think like the guide rate is whatever it was given, but it's actually being changed dynamically by on-step, which I think if that's the case, it's pretty smart. Okay, so now we understand quite a lot. By the way, this paper, amazing again. If you don't want to go through all of the calculations, there's also people that have given us a table of rotations at different coordinates of the sky. So your altitude and your azimuth on the left as rows, and if your azimuth is like 160 and your target altitude is 50, there we go. The derotation should be at this speed. I don't even know what the unit is. I don't care. But you can see you have tables of rotation values. And I suspect, because the calculation is actually quite complex, that any derotation software will actually refer to such tables, and it has to adjust the derotation rate like in real time to take into account your change in alt-azimuth throughout your session. It's really impressive stuff and quite a lot of fun, right? By the way, this information from Prima Luce doesn't come out of nowhere. There's like this quite old article about like guiding the Panther alt-az mount. This was a whole deal. I wanted one anyway. The Panther alt-az mount with PhD2, and we basically find exactly the same instructions here using the same. Like I'm almost wondering if like what. Wait, no, the screenshots are not the same. Yeah, the screenshots are not the same, but you can see it's very interesting. Now, one thing that they did not highlight on Prima Luce is this deck guide mode, and let's see, what do they have in here? Auto. So it's fine. Auto has the deck guide mode. Okay. That's good. Okay, we're good. Now there's another interesting article, by the way, that also has like those object position in the sky, and then the actual limitation in exposure time that you can take at some focal lengths. So you basically get the information from this table about the rotation angle or the rotation speed that you need to have, and you can expand that into like how long could you expose in alt-az without a derotator and without having star trailing due to rotation. So there's more to it, right? There's more to using to doing astrophotography with alt-az if you don't have a derotator. But now I had a final question, another final question actually. I was wondering, how do the professional stuff like Planewave, it's a maker that makes very expensive gear that is available to rich amateurs like not me, unfortunately, but like some of you, presumably. And so they have actually very large telescopes on alt-az mounts. They do have wedges available, but they have rotators, D-rotators, available as well. How does it work for those guys? I wanted to see. So I looked at their website. Very cheap, like 275,000 US dollars stuff. I mean, this is amazing. I mean, seriously, if you had the money, if you won the lottery, tell me you wouldn't buy this kind of stuff. I would. I definitely would if I won the lottery, but it's not going to happen because I never buy lottery tickets. Gambling is bad. Don't gamble. And yeah, poly markets, that kind of stuff. Yeah, don't do it. Anyway, going to the manual, I was wondering what I would see in there about auto guiding, and we see that we operate in an open loop tracking mode. Basically, what they're saying is that they're using encoders, right? It's the thing that makes sense. You have encoders on every axis. You have encoders in azimuth. You have encoders in altitude. You have encoders in rotation. If you have very fine encoders, you know exactly what's going on. And then you also have sky modeling, like we see with premium mounts like 10 micron, etc. With sky modeling, you know what the atmosphere is doing, so you know what atmospheric diffraction, or whatever, refraction, diffraction, I don't care, but what it does to your stars, and so you know exactly how to track perfectly across the star based on the atmosphere and based on your coordinates for the rotation speed that you need to get. And since you know all of that, it's all calculated, and you have encoders to double check that all of the equipment is doing exactly what you're telling it to do based on the sky modeling, based on where you're pointing, based on everything, then there's no need for guiding, right? So this approaches enhances tracking accuracy by enabling the system to account for positional deviations while keeping the telescope aligned with the target. And then it tells us closed loop tracking, which incorporates real-time adjustments based on actual exposure data, can be achieved through third-party software, ASCOM drivers, and auto guiders. But in this documentation, they don't tell you how. In particular, they have like some more information there, like we use open loop tracking, so we don't care about auto guiding. We don't support ASCOM move axis method, etc., etc. So it's not quite, that friendly to use like that. But we don't need to, because we have the encoders. As long as you have a good sky model and encoders, you don't need the auto guiding. But because the CPC, it does not have all of that, then you do need the auto guiding, and then you are restricted to the limitations that we went through for alt-az astrophotography. So it seems we've closed the loop, and now I'm really wanting to see how well this will perform at such long focal length in the real world. So please let me know if you ever get one of those telescopes down in the comments, because I think they could be a lot of fun if they work well. My guess is that Prima Luce, being Prima Luce, hello astronomers, we're able to test that it works well enough for long exposures, but I don't know about flexure when you start getting to very long exposures like 10-15 minutes in narrowband. So that will be very interesting to see. And then there's a tiny elephant in the room, an armadillo, let's say an armadillo in the room, which is, what about flat frames? I mean, typically if I rotate my camera, I take new flat frames with my optics. It's not always necessary, right? Sometimes you can reuse the same flat frames, even you have some rotation, but you're derotationing all the time. You cannot have flat frames for every single angle of your optics, although I guess you could take flat frames in advance if you never change your imaging train, and you take them for every 1 degree, and then you have a new software that can map the flat frames to the right light frames at the right angle, but that does not exist as far as I know. So if you own a plane wave system and you're not using a wedge, please let us know down in the comments what you do about flat frames. Maybe the optics are so good that we don't need flat frames in the first place. And that might very well be the case for the optics of the Prima Luce thing with the CPC Edge HD optics, right? But that's something that I was really wondering about, and I wasn't able to get a good information from my Google searches about flat frames on Alt As setups with a derotator. So again, if you have more information on that, let me know. My guess is just flat frames at beginning and or end of session, and then you just hope that it all works out. But yeah, let me know if I'm wrong. So there you go. This was my descent into madness. I went hiking in the mountains for 2 days, staying in the mountains one night. Yesterday and the day before yesterday, I had a beautiful view of Mount Fuji in the morning and the rest of the Tanzawa Mountains. Magnificent. And while I was hiking, walking, looking at beautiful landscapes, all the time I was thinking about how do you do Alt-Az astrophotography properly with auto-guiding? It makes no sense. So yeah, I went deep into the rabbit hole. With that, let me know what you think. Let me know if you have more information than I do. I'll have all of the links down in the description. I'll look forward to your comments. Thank you so much for watching till the end. It really helps the channel out. Like if you want to help even more, comment. And if you want to help yet more and you're planning on buying anything from Agena, High Point Scientific, etc., if you do so after clicking one of the links down that I have down in the description, it will help me out at no cost to you. And if you want to sponsor the channel directly, you can join my channel as a Patreon member, link in the description, or as a channel member. It's the join button next to the subscribe button. Thank you so much for your support. With that, thank you so much for watching. Don't forget, whenever you can, to look up at the stars, and I'll see you next time.